Something was observed, measured, and then walled off. No public images, no data release, no press briefing, just silence. James Webb Space Telescope pointed at it, captured infrared spectra, analyzed it, and then sealed the results. When pressed on why access is still restricted, the answer is familiar. The data take time. Give it a month or two to write the paper, maybe early October for the first glimpse of what this object really is. But the object is here now. So we ask again, if there's nothing unusual, why lock the data? It's not the first time. Webb has targeted oddities before, recorded them, and then disappeared behind a curtain of procedure, a silence that isn't accidental but built into the system. Contrary to public assumption, the James Webb Space Telescope isn't run solely by NASA. Its science operations are managed by the Space Telescope Science Institute, and the people who decide what's seen aren't elected or especially transparent. They're scientists, but also gatekeepers. Here's the process. Each year, selected teams win observing time. They submit lengthy, highly technical proposals. If approved, they get exclusive access to the data. Public telescope, private results. For months, sometimes up to a year, only the original team can view what Webb recorded. They can publish or they can wait. With 3 IATLAS, that's what happened. A team led by Martin Cordner secured time, scanned the target in infrared, captured a full spectral cube, over 40 gigabytes of raw data, and then set a proprietary lock. A 3-month embargo, the minimum allowed, and they took it. They could have waived it with a click. They didn't. Why would a team studying one of the rarest interstellar visitors choose secrecy? They'll say it's standard. They need time to analyze, and they deserve first publication rights. But this isn't a distant galaxy or a cool star. It's a passerby that won't return. Is this about academic credit or about results they're not ready to explain? Here's the wrinkle. Another team led by Matthew Pellico used director's time on the same object and released their data immediately. Same telescope, same target. One data set locked, the other open. Why the difference? What did the first team see that the second didn't? And it isn't just the data that's odd, it's the path. Most interstellar visitors blow in like cosmic tumbleweeds, tossed into gravitational chaos and slicing through at sharp, unpredictable angles. They arrive in a rush and vanish even faster. But 3I/ATLAS is different. Its orbit is retrograde, moving against the flow of the planets, rare on its own. Stranger still, it's almost aligned with the ecliptic, just 5 degrees off the plane where Earth, Mars, Jupiter, and the other major planets orbit. That kind of alignment is statistically uncommon. Most interstellar debris dives in from above or below the solar plane, wild and untamed. 3I/ATLAS, by contrast, comes in like a probe, flat, steady, deliberate. Then there's its route, Mars, then Venus, then Jupiter, 3 encounters in that exact order, as if sampling the inner solar system. Mars the red desert, Venus the hell world, Jupiter the gas giant, a tour of extremes. The sequence is not only rare, it runs counter to the usual gravitational flow, neither falling inward nor being dragged along. It feels as if 3I/ATLAS chose its path. Avi Loeb, the Harvard astrophysicist known for pushing boundaries, did the math. The odds of this trajectory, with this timing and proximity to Mars, Venus, and Jupiter, happening by chance, are about 1 in 20,000. Peer-reviewed, debated, but not ignored. Still, the mainstream response has been shrugs and dismissals. Coincidence, they say. Natural dynamics, not intent. Yet consider the pattern. 3 interstellar visitors in just 8 years after centuries of silence. Oumuamua, Borisov, now Atlas. Each with anomalies, each slipping through too quickly to catch. Have such objects always passed unnoticed, or are we entering a region where they drift closer? If so, what else is out there? This doesn't feel like mere chance. It looks like choreography. The same corridor, the same angle, the same dance. Comets are random. Debris is chaotic. 3I/ATLAS feels designed. A flight path, a probe, a scan. And if it's scanning, someone or something might be listening. The object is here now, and soon it will be gone. 3I/ATLAS is moving at nearly 60 kilometers per second, fast enough to escape the sun entirely. Its path is hyperbolic, open, never to return. Worse, we're about to lose it. In late October, it reaches perihelion, its closest approach to the sun, when it should be most active and revealing, shedding dust, ice, and gas under intense heat. But from Earth's perspective, it will sit directly behind the sun, blinded, blocked, unobservable. Ground-based telescopes will be in a total blackout. Hubble will be overwhelmed by glare. Even Webb at L2 has pointing limits to protect its optics. The timing couldn't be worse. There is a sliver of hope. 2 spacecraft already en route, NASA's Psyche and ESA's JUICE, will pass within about 0.3 to 0.4 astronomical units during the peak. Close enough to see it, perhaps even study it, but neither was built for this. Observing 3I/ATLAS would mean diverting, burning fuel, changing course, accepting risk. In deep space, every maneuver is a gamble. Every kilogram of propellant is survival. Will they take the shot? That choice lies with mission teams and managers who may not believe the risk is justified. But what if this is our only chance for a close look? To capture real-time footage and probe dust, light, and structure from within the object's own shadow. There's one more radical idea. Avi Loeb has proposed using Juno, now orbiting Jupiter, for a last-minute slingshot toward 3I/Atlas. On paper, with perfect timing, Juno could intercept in early 2026, the first pursuit of an interstellar visitor. In reality, Juno's main engine is compromised, its fuel limited, and the mission stretched thin. Many call it fantasy, too risky, too late. But if it worked even once, it would be historic. Because once Atlas passes Jupiter, that's it. It fades, the coma shrinks, and its spectrum dissolves into the background noise of deep space. Right now, the object is here, speeding through space, and soon it will be gone. 3I/ATLAS is flying at nearly 60 kilometers per second, fast enough to escape the sun entirely. Its path is hyperbolic, an open trajectory. It won't be coming back. Worse, we're about to lose sight of it. In late October, 3I/ATLAS will reach perihelion, its closest approach to the sun when it should be most active. Venting, dust, ice, and gas. As intense heat exposes its interior, but we won't see it. From Earth, it will sit directly behind the sun, blinded, blocked, unobservable. Ground-based telescopes face a complete blackout. Hubble will be overwhelmed by glare. Even Webb, a million miles away at L2, has pointing limits to protect its optics. The timing couldn't be worse. We wait years, even decades, for interstellar visitors. And now that one arrives bright, close, and mysterious, we lose it at the very moment it could teach us the most. There's a slim chance, 2 spacecraft already en route, NASA's Psyche, bound for a metal-rich asteroid, and ESA's JUICE, headed to Jupiter's icy moons, will pass within about 0.3 to 0.4 astronomical units during the object's peak activity, close enough to glimpse it, maybe even study it. But neither mission was built for this. They'd need to divert, burn fuel, change course, each step a risk. In deep space, every maneuver is a gamble. Every kilogram of propellant is survival. Will they take the shot? That call falls to mission teams and managers who may decide the risk isn't worth it. But what if it is? What if this is our only chance to see an interstellar visitor up close? To capture real-time footage and analyze its dust, light, and structure from within its own shadow. There's one more radical idea: using Juno, now orbiting Jupiter, for a last-minute slingshot toward 3I/Atlas. On paper, a perfectly timed boost could enable an intercept in early 2026, the first pursuit of an object from another star. In reality, Juno's main engine is compromised, fuel is limited, and the mission is already stretched thin. Most call it fantasy, too risky, too late. But if it worked even once, it would be historic. Because after Atlas passes Jupiter, that's it. It fades, its coma shrinks, its spectrum sinks into the background of deep space. It becomes just another point, another ghost, lost in the void. And we'll be left staring at our hard drives, wondering what we missed. There is no rewind in space, no second chances, only motion and silence. So here we are with humanity's most advanced telescope trained on a visitor from another star. And what do we get? Nothing. Not from failure or corrupted data, but from a choice to stay quiet. They say it's standard protocol, a matter of scientific priority, giving researchers time to publish. But this isn't a distant quasar or a star forming 10 billion light-years away. It's here, inside our system, and the clock is running out. The data exist, the spectra, the high-resolution infrared maps, real and locked. Maybe they show nothing but dust, ice, and rock. Or maybe they don't. Maybe Webb caught a tight infrared line, a faint spectral spike we weren't ready to face. Maybe the silence isn't about hiding, but about buying time, to explain, to prepare, to rewrite the story before the public hears it raw. What if the truth isn't just scientific, but existential? What if something out there isn't merely passing through, but watching, and has been for longer than we think? We once believed the universe was quiet, empty, predictable. That illusion is fading, leaving us with the unknown. So ask yourself, if this isn't a cover-up, why does it feel like one? And if the sky is truly silent, why are we told not to listen? If you're still listening, still watching, still questioning what's out there, add your voice to the space pulse. Leave a trace, because the silence won't last forever, and the next visitor might not knock.